This lesson is on small angles, and you need to have your calculator with you for this investigation that we're going to start off with at the beginning. So first we're going to convert 3 degrees, which is a small angle, into radians, and to do that you multiply by pi and 180, and that is going to equal about 0.0524 radians to 4 decimal places. So 3 degrees is 0.0524 radians. Now let's find sine of 0.0524 and let's find tan of 0.0524. So sine, maybe if you put 0.0524, if you store that in your A memory, then you can just press, and remember to store it in your A memory, you're going to press Shift Store A, and to get that number back, you're going to press sine of alpha A. And when you do that, you should, let's see what we get to 4 decimal places. Oh, we get 0.0524. Same number. That's interesting. Let's see what we get when we do tan of 0.0524. So this is where you would like to, where you need to press tan of alpha A, and we get 0.0524. That's interesting. Let's see what we get when we press cos of that small angle. And cos is not 0.0524. Cos of 0.0524 is 0.9986. So I guess that's roughly equal to 1. Yeah. So for small x, so for small angles, what can you say about sine x, tan x, and x? Well, I think that should say cos x there. Ooh, that's moving. Well, we can say that sine x is approximately equal to x, tan x is approximately equal to x, and cos x is approximately equal to 1. So is it true that for small x that cos x is approximately equal to 1? Yes. So that's for small angles. And this is an example from your textbook. The planet of Alpha Zeta, so this is the planet Alpha Zeta here, in a faraway galaxy has a moon. Here's the moon, with a diameter of 145,000 kilometres. If the distance between the centre of Alpha Zeta and the centre of the moon, so that distance there is 12.8 times 10 to the power of 6 kilometres, find the angle subtended by the moon. So they're asking us to find this angle theta. Find the angle subtended by the moon at the centre of the planet in seconds. That's subtended by the moon. That's the angle there. So, okay, so looking at this little triangle here, we'll call that a right angle there. Then this distance here will be the radius, so it'll be half of 145,000 kilometres, which is 72,500 kilometres. Is that length there? And maybe we'll just call this angle here alpha. And you can see that 2 alpha equals 1 theta, because theta is the whole angle there, and these two triangles are congruent. So 2 times alpha equals theta. I'll just write that down so we remember it. Theta equals 2 alpha. Okay, so in our little right angle triangle, we could say that tan alpha is opposite over adjacent, so the opposite side would be 72,500, and the adjacent side is 12.8 times 10 to the power of 6. So putting that in your calculator, you will get alpha is 0.00566. Sorry, that first 0 looks like a 6. That's a 0. Alright, now that is alpha in radians. Okay, and the question is asking to find the angle in seconds, although I think that really should say find the angle in minutes. Because remember, a degree can be split up into minutes, seconds, etc. This is going to be a small angle, so smaller than 1 degree. So we'll go to minutes. Alright, so if alpha, our answer for alpha here, that is in radians, how do we convert radians to degrees? Well, we multiply by 180 on pi. So in degrees, 0.0056 is going to equal 0.32 degrees. 0.3245. Just making sure you do this on your calculator as well. So that's what alpha is. So that means theta, which is that whole angle, is going to be 2 alpha. So times that answer by 2, and you'll get 0.649 degrees. And if you press the degrees, minutes, seconds button on your calculator, that's the one that looks like some little eyebrows, like that. You guys know that button. Then you can see that 0.649 degrees is equal to 0 degrees and 38 minutes and 56.57 seconds. So rounded to the nearest minute, it's going to be 39 minutes. Okay. Alright, so now what you know about the sine curve and the cosine curve, this is a little proof for you. So, I think then it's all from your textbook. So you know the sine curve, that as h approaches 0, so we're talking about, limits here. So as h approaches 0, so or you could say as x approaches 0, you can see there that sine x or sine h approaches 0. Okay, on the cosine curve, however, changing colours. On the cosine curve, you can see that as h approaches 0, so as x approaches 0, so we're going this way here, cos x is approaching 1, because you know the amplitude there is 1. So that's an important concept to know. And we're going to use that now to work out this relationship down the bottom here. So let's have a look at this diagram here of this triangle, where AB is an arc of the unit circle. So that's a unit circle. That means OA and OB are both 1 unit. That's what unit circle means, that the radius is 1. O is the centre of the circle, and AT is the tangent at A. So AT, that's the tangent. Now this is saying that the area of triangle OAB, so that triangle there, and the area of triangle OAT, the big triangle there, well, this area of the sector is, the area of that sector is in between the area of the small triangle and the area of the big triangle. So the area of sector, OAB, is talking about that sector there. And you can see that that area of the sector is bigger than the small triangle, but less than the big triangle. Okay, let me just rub some of that stuff off. It's not working very well. Okay, so the area of the sector OAB, using the formula that you know for the area of a sector, which is half r squared theta. Now you already know, remember, that the radius of OA is 1 and the radius of OB is 1. So half r squared theta is going to be half times 1 times 1 times theta, and theta is represented by h. So that's where the half h comes from, half r squared theta, area of a sector formula. Then this small triangle here, triangle OAB, the area of that triangle is half AB sine C, and where A and B are both 1. So there's our small triangle. And so we get half of 1 times sine of that angle, which is h. That's where half sine h comes from. Then let's look at the bigger triangle there, which maybe I'll outline that in green. There's the big triangle. Area of a big triangle, well, you can see that there is a right angle in our big triangle there. So the area of a triangle is half base times height, where the height, well, the base you can see is 1, and then the perpendicular height will be this length over here, AT. And the length of that side, AT, let's have a look. See how in here they've got tan H? So let's find a relationship. Tan H in the right angle triangle, the big green one, is opposite, which is AT, over adjacent, which is 1. So then we can say AT equals tan H. So the area of this triangle OAT is half base times height, where the base is 1 and the height is tan H. So the area of the big triangle is half tan H, which is where that formula there comes from. Now you can see here this relationship. If we multiply everything by 2, that will get rid of the halves. And if we also divide everything by sine H, we get this relationship here then. And this is saying, remember, that as H approaches 0 up here, we were saying as H approaches 0, cos of H approaches 1. Therefore, so cos of H is approaching 1, and 1 divided by 1 is 1. So this is saying that H on sine H is in between 1 and 1, which means that as H approaches 0, H on sine H must also approach 1, which is what this is saying here. So that's all you really need to know for 2 unit, that this relationship here. Might just put a box around it. As H approaches 0, H on sine H approaches 1. But the extension 1 girls actually need to use that relationship, and on the next slide there's some examples. So the 2 unit girls don't really need to know how to do some examples like this, but I guess it would enrich your learning. Using the fact that as H approaches 0, or as X approaches 0, sine X on X equals 1. And we just had a look at the proof for that using the area of that sector there in between that small and the big triangle. So, now in order to use this, what I guess we could call it a special limit, is this angle here and this angle here need to be the same angle in radians. So if you have a question like this where we're asked to evaluate this limit of sine x on 4x as x approaches 0, remember we need the same angle here. So what we can do is we can take this 4 and move it outside the limit. So what I mean by that is saying that this is the same as the limit of 1/4 times sine x on x, and that's 1/4 times the limit as x approaches 0 of sine x on x. And now you can see that our angle on both the numerator and denominator are the same, so we can use this special limit. So the limit as x approaches 0, sine x on x, you know that's equal to 1, and that you got 1 times 1/4, which is 1/4. Alright, the second example here, tan of theta on 3 and theta. So this special limit also not only works for sine but also for tan. You might remember in the first example when we were evaluating for the small angles, sine of x was equal to x, tan of x was equal to x, but cos of x was approximately equal to 1. So we can use this special limit here, the same thing but just with a tan there. So that means these angles here need to be the same. So means we need to change the angle on the bottom from theta to theta on 3. But we can't just change it to theta on 3, that'll change the value of it. But what we can do, because if we had it like that, then that equals 1. So what we need to do is, it's kind of like when you are modifying those integration questions, and you would like slightly modify them by putting a number out the front of the integral and a number inside to make it easier to integrate. So we can put the third there like that, because then you can see that that 3 there and that 3 there would cancel and we get straight back to the original question. And then what we can do is just move that third out the front of the limit, just how we moved the 1/4 out the front in the first question there. So we're going a third times limit as x approaches 0 of tan theta over 3 over theta on 3. And then you can see that this is equal to 1. So we've got a third times 1, which is just a third.